Hey everybody, this is Larry. This is day 28 of the Leetcode Day Challenge. Hit the like button, the subscribe button, join me on Discord. Let me know what you think about this one. It's a hard problem, 834 sum of distances in tree. The contest is in about 2 hours, but I'm going to skip it today. And it's the first time I think I'm skipping it for a reason that isn't that I'm busy. And as some of you might know, I signed up for a half marathon, 13 miles or 21 kilometers. Just like 2 days ago now or something, right? And I am not prepared for it. I mean, I think I'm physically prepared for it, but waking up early is a disaster. So I'm going to need to try to skip the contest because the contest actually, it gives me a lot of adrenaline, and I end up staying up a little bit later than I would like in general. And for this one, I have to wake up really early. The ones at 7, I have to wake up at like 5 or something. So So yeah, so if you're waiting for the contest videos, it'll be tomorrow, probably afternoon in New York time after I get back and probably take a long nap and all these things. So yeah, so also, show me some support for my run. I think for tomorrow's video, I'll probably post some photos or something. So I'll let you know the daily video. So definitely, yeah, I'm very excited. It's my first race ever, and I don't know what to expect. So I don't know, but hopefully I won't embarrass myself too much. And figure things out. So okay, let's take a look at today's problem. Long intro. Hope you enjoyed it. Let's see. We have an undirected connected tree of n nodes. Okay, there's a tree. We have edges that denotes the tree. Sum of the distances between ith node in the tree and all the other nodes. Oh, wait, what? Answer sub I is the sum of the distances of between the ith node in the tree and all the other nodes. So the 0, okay, so 0 is going to be 1, 8, okay, okay. This is a hard problem. I don't know if I did it the correct way before, to be honest. Because there are a lot of these tree problems that I think a lot of us were just very wrong about the complexity. There is this. Let me bring up the drawing board real quick. So the reason why I say this is because I think a lot of the past problems, and if you watched an older video of this, you may actually get the wrong answer. And I didn't know I was wrong at the time, to be honest. And it's just, but basically the idea with here is that you have this tree, right? So the idea is that, okay, you have some nodes, you have a tree, right? And the idea is that you cache based on the edges and not the nodes, right? So for example, if you want to cache on, let me add a couple of nodes, hang on. If you want to cache on, or memorization on say this edge, there are two answers, right? There's this way and this way. So this going this way, you may have, say, there's 3 nodes, and maybe you could do sum of distances like going up or something. And if you kind of just do that like a depth first search going that way, then you may get the answer. And the same thing for this one, which actually coincidentally is also 3 nodes, and then you kind of sum the distances or something, right? Okay, and then you memorize both ways so that when you kind of aggregate together, in theory, each edge could only go once, but that's not quite what happens. What happens actually, or you would think that that's what happens, but that's not what actually happens. What actually happens is that when you have, depending on how you implement it, and I've been bad about it, is that you have this thing called, what do I call it? The star graph or star tree. Is that, for example, if you try to memorize one edge, let's say this one, then if you want to memorize this one, this goes to this node, and this node will do a for loop on all of these, right? So it's going to do an O of n for loop, and yeah, and that'll be O of n. So, but that's okay, right? Because this edge is already used up, so we should care. However, the problem comes from that if you, let's say now you start from this node, right? And now you're looking at this edge actually still calls into this, and even though and depending on how you implement it, we still calculate the O of n loop for all the edges, and that's going to be O of n as well. So if you kind of think about it that way, that's going to be n squared, because for each of these outside nodes, we do O of n because of how you, because we don't cache on the node, that's going to be it. So that's the difficulty with this problem, and I don't know that in the past I've done it the correct way, to be honest, because I think I give a lot of credit to Josh Chen, numbers, or am I doxing him? Hopefully not. I think he has it proper-sized anyway. But yeah, I give him a lot of credit for, I think, a couple of years ago, and that's why I don't remember the time. That's why I checked it, even though maybe it's a little bit half cheating, because I think that's around the time, or this is before the time where I realized this edge case, and yeah, and basically it's easy to make an n square edge case, right? No pun intended, even though it is maybe a good one. So how do we do it? There are a couple of ways you can think about it. The way that I would think about it is called tree rerooting, right? Is that basically we root it with the tree in one root, and then we try to do the math on what happens if we reroot it another way, right? I'm actually very weak at this. I mean, I would say I have gotten practice a few times, but I am still very weak at this. So bear with me, and hopefully this video will be good enough that next time I do a little bit better. Okay, so the first thing that we want to do is, the idea behind tree rerooting is the same idea that we want to figure out. N is 10, or 3 times 10 to the 4th, but whatever n is, obviously n squared is too slow. If n squared is too fast enough, this is not an interesting problem, right? You just do a depth first search on each node and then root it, literally rooting it on each node, and that's not interesting enough, right? And so to make this work, it means that, okay, for each of the n nodes, well, one is that we root it at one node. It doesn't matter which one, because it doesn't really matter, right? Because you have to do it for one of them. So that's going to be linear time for whatever reason. You have to look at every, n-ish, right? And then now the cost of rerooting this, expressing the answer in another root, has to be, O of log n or faster, so that you get the combined time of O of n or n log n, right? So that's basically the general idea. This idea happens a lot in different forms, but basically this is how you can get the complexity to be fast enough, right? So these are kind of the implicit constraints that you get. Okay, so the first thing that we want to do is we want to calculate the answer for one node. So let's do that. And this is going to be a little bit detailed, so I'm not going to do a bonus question. I know that I often do a bonus question, but I'm not going to do a bonus question today. Like I said, I'm also trying to go, I wouldn't say I'm trying to go to sleep. I mean, I am trying to go to sleep early, but realistically, it's not happening. But I'm just going to rest around and just, watch some silly YouTubes, and hopefully I get enough sleep that way. But okay. So first of all, we want to, the key thing here is the same thing that I talk about in what I said about O of n, and then you calculate it once, and then you try to shift the answer for each of the thing. In this tree, it's called rerooting, but you can also imagine the same thing with sliding windows problems or contribution problems, where you calculate the answer for one node or one index, and then it takes only increment, like log n or O of 1 for each incremental fix change, and we want to do something similar for n, for this tree, right? And of course, it requires us to know what the data structure and what to store so that we can be reused. Right now, I don't know yet, so let's do that, right? I would also say that some people are very good at doing maths, because there may be an easier solution, but this is the one that I want to practice, because I think sometimes people are just very good at stuff. Okay, so so we have an edge list, so let's actually convert this to a adjacency list first, just so that we can actually use it in a good way, right? So this is an adjacency list of the tree. And then now we want to just do initial recursion, right? I never know how to name these things. In contests, that's why I name everything Go, just because I don't have to think about it. But let's just say calculate is also like a useless name, to be honest. That's why I'm like, okay, fine. Let's just say get distance. I don't know, right? And because they're all the same, we'll just do it for node 0. Right, I just want to make sure that this is 0 indexed. And then here we have node and parent, because it's a tree, so that we don't go the same one, right? So here, for what I want to do is solve it for one node, right? So yeah. Right, so distance 0, 0, right? For v in adjacency list of node, if v is not parent, then distance we added to get distance of v, and then node is the parent, and then we return distance. And then now we can say answer is equal to 0 times n for just, I don't know, whatever, right? Is equal to this thing, and then, you know, maybe we'll return -1 so it'll be more obvious that we haven't finished it yet. Just want to see if the first node is correct. Now, because everything is 0 because I don't return anything. This is get distance plus 1 for each node that we go down, because that edge is adds 1, right? Eh? That's awkward. What? Oh, I mean, it's definitely returning it as 0, but why? Does this not? That is weird. Empty, huh? 0, 1. Oh, what am I doing? Whoops. Okay, I mean, I don't know. I'm glad I'm not doing the contest, because that is a very silly mistake. Okay. So is this right? I mean, clearly not, but so it goes 1 for 1, 2 for 2. Oh. It's not 1, it's the sum of the distances, right? How did I get that in one thing? Actually, I don't know, but it doesn't really matter, because there are different ways to represent it, so I don't even worry that much about it. In a sense, right? Yeah, let me try to think what I can. I mean, we can add a distance thing, but it's fine. The structure is right. Yeah, I mean, it's an easy fix, but I'm just trying to figure out. So, but now, all right, let's say this is correct, this is not, but that's fine because it's not what we want to do anyway. Is that okay? So then now, looking at this example 1, right? The thing that we want to calculate is how does the answer change when we go from 0 to 1? Let's say we have the answer for 0. Well, from 0 to, if we kind of move the root from 0 to 1. Then that means that the answer that we get for 0, all the nodes that are not on the branch of or on the edge of where the 1 is, so all the other so in this case it'll be the let me just draw it out. Hang on, sorry. I think this is worth drawing out. All right, let me. I mean, the code we have so far is not quite right, but it's approximately right. That's the structure we want, and that's what I care about more, because we have to figure out what we actually care about, right? And here now, let's say we have this, right? So then let's say we have the answer for whoops. Change the color real quick. Let's say we have the color for 0, right? And now we want to change to 1. Well, everything that's on the other side of the other edges. What happens? Well, what happens is that it got further away by 1 edge, right? So that means that if we know the answer for, and this generalizes beyond 2 edges because this is not a binary tree. So basically, for example, let's say we have 6, 7, 8 or something like this, right? What this also means that all the other, and this one as well, everything here is +1. So that means that we have to keep track of the number of nodes on each of the branches that go down from 0 and the total distance. Because then now we could add that to the number of nodes. So that means that we need to keep track of 2 things for each node, or for each root. Well, to keep track of 2 things for each root and the edges that go out. And yeah. Right? It's very awkward. I don't know. This is why I need more practice, though, to be honest, right? But that's basically the general idea. So then now here, maybe we, instead of get distance, we get info or something, right? And then now, what we want is, we want to count the number of nodes. So here we can say nodes is equal to 0 times n, and this is a subtree, maybe let's call it subtree. Basically, how many nodes are in the subtree of the index of where the root of the tree is indexed, right? Not the root of the tree, the subroot, or the, yeah, because the root of the tree is 0, right? That's what we want to do. So yeah, and then here, so there's the number of nodes, and then maybe total distance, right? Which is the answer that we care about, sum of distances, right? So then here maybe we have another one, distances is equal to 0 times n, right? And then now we can get info of 0, 1, right? So then now here, for each node that is a child, we can say subtree sub node. How do we want to write this? Because we want to write it out, right? Well, here maybe we don't return anything. Let's just forget about the return for a second, right? So we just do this recursion, right? And then now that means that afterwards, subtree sub node, we can add it to the subtree sub v, right? Because that's just how the subtree part works. And then distances sub node, we add distances sub v times, or not times, but plus subtree of v, right? Because the distances, the sum of the distances, for example, looking at example 1 here, the distances of 2, we add it to the number, because we have one more distance away when you go recursive back up. So then now, you know, we have this. But yeah, but otherwise, let's say subtree of node is equal to 1 for this current node, and distances of node should be, you know, just 0, just because. Yeah, and then now we can do a recursion. Oops. And in theory, we can do 0 is equal to distances of 0. We'll see if this works a little bit better, now that we have a little bit better understanding of it. Okay, so I mean, now the first node matches. I mean, obviously we don't expect the other ones to, but yeah, now we have to figure it out. Okay, now this is the first recursion, right? And then now we have to do the rerouting. Yeah, and then now basically, and we can do this recursively, and I mean that's how it usually is done. But and I don't, I mean, don't hold me as getting everything correct just yet, because like I said, I am trying to practice this and I'm not very good at it. Or like, I feel like I can get it right, but it's just, it takes a while. So forgive me. But yeah, okay, so that means that now, and because there are supposed to be more parameters in the rerouting, which is basically saying we want to pass in all this this information of the other stuff into the thing, right? Because basically now, okay, let's say we have for v an adjacency list of node, right? If v is not equal to parent, then what happens? But basically, the idea here is that when we are at this current node, we are saying we want to reroute it from the parent, right? Not from the root 0, but from the parent. So, so now, what happens? So basically now we know that we have two information here, right? It's the subtree and the number of nodes and the distance of node, right? So that means that, do I have the drawing thing up? Okay. So here I'm using kind of this is how I visualize it, is that, okay, like I have a physical example or visualization example, and I go, okay, let's say I'm going from 0 to 2. What changes, right? What changes from 0 to 2 would it be that everything on the other subtree, and the other thing, everything on the other subtree is just subtree of node minus subtree of v is so that other nodes, it may be off by 1 because maybe I overcount. I think this does not count 0, so maybe it's plus 1 or minus 1. But I want to go with the idea first, and then we'll think about it. I think this, because this includes the 0, and this includes, so basically this is all the other nodes that are not, so if we're talking about 0 to 2, then this would be 1, because all the other nodes are just 1, right? Or node 1. Okay, so then we have all the other nodes, and other nodes, we know that their distances yeah, so then it is just, so we already have the sum of the distances, which is distances sub node minus subtree of v would be the sum of all the differences. Oh, sorry, not subtree, sorry. Distances. This is the distances of all the other distances, right? So then now, other distances plus other nodes is going to be the answer for distances. I guess this is answer sub v. It's going to be equal to, well, I mean, maybe not just equal to, but part of it is going to be all these other nodes moving 1 foot away, right? But the other thing is that here, let's say you're going from 0 to 2, so then the 0 and 1 will go 1 farther away, but your subtrees get closer, right? So that is the big part of it, is that now, the subtree of 2, all the nodes that are in the subtree of 2 gets a little bit closer. So that means that this is this minus subtree of v, I think, right? Maybe? Oh, yeah. Oh, no, yeah. Because, well, it is distances of v plus the distances of v, because that's what we have, but then minus subtree of v, because it gets 1, each node gets 1 distance closer, right? So that's basically the idea. Maybe it's off by 1 or something, but let's just give it a spin real quick. I mean, I'm not confident about this at all. Like I said, I need more practice, but it will serve to kind of just give us like an idea to see how close or far I am. Okay. Now I've done pretty okay, right? So for 1, that's true. For 2 is also correct. But why is it wrong for 5? Oh, because it's subtree of node. Okay, so the reason why this is why I said that I need to maybe pass something in. There are 2 ways to do it. I always feel like I choose the harder way, so we'll see. But the reason why this is let's say now we're still looking at this, so visualize as I kind of pointed out. Let's say we go from 2 to 4, what happens? Well, now all this does is what this does is what I did anyway, is saying that, okay, from the 2, So all the other nodes that are not in the subtree of 4 is +1, but that's not what my code is, right? My code is that all of the nodes that are in the subtree of 2. So maybe I just need to change this to 0. Maybe I'm off by a little bit though. I mean, I could be off by 1. I think that's what I was saying. Maybe. Why do I have 12? Because yeah. So subtree of. Okay, so other nodes is going to be all these other ones. Let's just print it out real quick. Print node, other nodes, other distances. Right. Oops. I see why. I mean, I think other nodes is correct, but other distances may not be. I think that's where I'm messing up. Because the idea here is that, okay, the count of the nodes, this is actually correct, but the distances is not from 0, because that means that everything from the other side of, because a lot of things shift, right? So I have to kind of reconcile. So this is not quite right. Because other distances is wrong, because from 0 to 2, a lot of things got subtracted, but from 2 to 4, things got added again, right? For example, if we look at this, we go from 0 to 2. The distances from 3 and 5, they got one smaller, right? But if you go to 4, well, it gets one bigger again. So the other distances isn't quite correct. I have to think about another way to do this. Yeah, so I think that's why I initially did it with the root or with the parent, but I was hoping that that would be good. Okay, so let's say we have the parent, but now, so then that means that for here, for us to figure out what to do, and here, because we only rerouted from the parent, from here, what information do we need? Well, in this case, if let's say we're going from 2 to 4, we need the information from 0 and 1, right? So that means that we need, to pass in all the other stuff, right? So that means that, okay, probably other nodes and other distances here, and then this is like parent nodes, parent distances. I don't know if this is a good term though, but yeah. And then now we add, this isn't enough either, I don't think, and also I did it in the wrong order anyway, but I think I have to add it, because other nodes now we have to add parent nodes, and other distances we add parent distances here. But here now we have these other things. Yeah, I guess I could just write it here, right? So other nodes, we add the parent nodes to add in. We add the parent distances as well. And then it's just, then here, we don't have to. And then now the answer, is that right? Or am I still? Oh, yeah. No, I'm still double counting a little bit. How did it? This is the number of nodes. Is that right? Let's also print this real quick, and then we could. So the reason printing it allows us to kind of just audit this real quick, right? So node 0, other nodes, other distances. Oh, I guess it's node and v. V matters for the purpose of this one. 0 to 1, there are 5 other nodes. I guess that's true. Distances 8, probably right. I didn't check that. Okay, fine. So 0 is true. That's good. And then now it goes from 2 to 3. Why? Oh, because I guess 1 doesn't do anything. Just 1 doesn't have a child. Okay, fine. So then now we go to 2 to 3. 2 to 3. Other nodes is 5. Is that true? 1, 2, 3, 4, 5. I guess that's true. Other distances. Node 2. Oh, this is solving for 3, right? So 3 other distances we have. Other nodes is 5, 1, 2, 3, 4, 5. It's true. Okay. Each of this is parents distances. Okay, that's fine. Okay. Sorry, I'm thinking real quick. Okay. 2, 3, 5, 8. 8 is the other distance. Is that true? I think other distances, the way that I have other distances isn't quite right. Okay, what is distance of node 3? So 2 and 3. Okay, so what is 3? 3 should be 10. I have 8. And this is the number of nodes not including re. Is that right? Is that right? No, this should be subtracted. Isn't it? No. Even worse. But I think it should be though, because this is the number of nodes that got closer. Because the other nodes are the distances that got farther. So answer sub v should be the answer of nodes that are closer, right? Anyway, I get the idea about this problem, but you know, as you can see, I am struggling a lot. That's why I need to practice, I suppose. But okay, other distance, is this right? I don't even know. Okay, so distances of node of 2 is going to be correct with, oh, maybe not. Well, I think that's after I added a funky thing. Oh no, wait. Oh, that's because I, okay, let's just keep this for now. All right. Right, 2 is 6. Answer is 6, but the 2, and I do this recursion backwards. Oh no, I just printed backwards. I mean, I think okay, fine. That's why I think it looks funky. Okay, 0, 2, 2 and 5. Is that true? The 2 nodes, and now the distance is 5 because 2 of the nodes got farther and 3 of the nodes got closer, right? Or 4 of the nodes because you include the root, so yeah. Okay, let's say that again. Okay, so other distances is 5. Why? Actually, That shouldn't be 5. I think I just got lucky. Other distances should not be 5. Oh, but it's plus parent distances. That's why. No, parent distance is 0, so this isn't right. Why? How do you get 5? Distance of node, which is 0, that's going to be 8 minus distance of 2, which is 3 because we only have 3 child, so that's 5. Is that right? No, I don't think so. I think this whole formula is weird. Distance of 2. Okay, I think this, I think I just got lucky with this answer. I think that's why I didn't get it. Okay. I was hoping there's some symmetry, that's why I kind of did it this way, but this is clearly wrong, right? So distances of V so other distances is going to be, is that 5? How do you get 5? So okay, wait, so 1, 2, 3, right? So it should be only 3 is the other distances, and not even. I think it's just 1, and then oh, I think I have to subtract out the fact that this is smaller. So then this plus subtree of V. Okay. I mean, this isn't right, but hopefully it's a beginning, because then now I could fix the other stuff. I think I had some other stuff that was wrong, and it kind of canceled out in a weird way, which is why. Okay, so other nodes and other distances. Is other distances finally right? 0, 1, 5. The 5 other nodes, correct. 7 other distances. This other distances not including this. So wait. Yeah, I think that is actually correct. It is 7. But then now it's 7 plus 5. Right? Because we have 5 nodes. Do I need this? Maybe I just kind of factored that in. Okay, so at least we got the 1 node correct to 12. But then now the 6 node is incorrect. But that's fine. Making some progress, at least in understanding. Okay, so then now for node 2, we have other nodes. There are 2 other nodes. Yep. The other distance is 1, which is true. Okay, so we're good here. So they get yeah. Okay, so they get further away, right? So this is what represents this, and this is how you get 3. It's not correct yet because it doesn't include the subtree of V, right? So then now distances of V minus subtree of V, because isn't that what I had though? And then I think this is wrong. Why would that give me a negative? Distances of V. Distances of V should be 3, is it not? Let's check it out. Because it should be 1 away. Okay, distances should be 3, and that's correct. But subtree is 4 because it contains. Oh, why did I do so? Oh, because I contain minus all the nodes. So distances of V yeah, because the current node is technically 0 distance away, so that's why. And the 0 node is not going to move closer, so it's minus this subtree minus 1, which is confusing, but okay. Okay, so then I think this is now right. The going from 0 to 2, there are 2 other nodes, they're 1 distance away. Distance of V is 3, subtree is 4. That is actually correct. Well, is it? No, because you could just add the distances of v because we don't care about these things. Because distances of v is already the distances from 2. We already know the answer, so we don't need. Okay, so at least we fixed that one. Okay, yeah. That makes sense because we're trying to figure out what is the sum of the different distances from v, and we don't need to change it. We don't need to shift it because we're already there. We just went to 2. Okay, yeah. And then now the tricky part, hopefully, which is the ending, is we go from 2 to 3. 2 to 3, we have other nodes. We have 1, 2, 3, 4, 5. 5 other nodes, that's correct. Other distances, 3 sounds incorrect, to be honest. I think this is where the parent stuff have to be careful a little bit. Let's remove these real quick. I think that's fine, it looks like. Okay, that means that there are 2 parent nodes and 1 parent distance. Is that right? Going from 2 to 3? I mean, at 2, that is correct, but other distances is not correct, I don't think. Wait, let's see. 2 to 3, 5, where 5 nodes, distance of 3 is definitely incorrect, right? It is incorrect. Okay, distances from 2 is going to be 2. Okay, that's true. And they grow 1 more. Wait, do they? Oh, no, this is subtree of v, so we don't care. The distance of node. This is such a. Alright. Distance of node is going distance of 2, which is 3, minus the subtree of 3, because we get 1 closer. But we have to get all the other subtree of. I think I mixed 2 things in here, that's why. Because I think here, what I'm saying is distance of v plus subtree of v is because. Wait, what does this mean again? Oh man, I am now forgetting. Number of other nodes is right. Okay. But okay, let's the 2. I don't know why I'm having so much trouble today. Alright, so the 2, we have 2. We have 5 nodes. The 2 and the 1 is not enough, I don't even think. But because the distances is actually parent distances plus parent nodes or something. I don't know if that fixes it, but I mean that fixes that. Is that enough? Is that what I'm just forgetting? Maybe, yeah, maybe I just didn't move the parent distances by that. Okay. I'm not confident about this one, to be honest. I think this is rough. I mean, the structure is roughly right, but like I said, you have to be really precise, and clearly I'm not. I'm just gonna submit though because I am lazy. Yeah, let's give it a submit. All right, so I guess that was it. I just kind of forgot to advance this part. I thought a lot of. I mean, I knew that was part of it, but I didn't think that was enough. That's why I didn't fix it yet. And I think I confused myself because of how long I spent on this problem on this part. But all right. So this is tree rerooting. I don't know that there's a good idea article about this idea, but basically the idea is just to kind of figure out how all the other tree works and then calculate how the differences move, right? And you can kind of see how I did it. And this is a very long video, so you really get to see how I do it. But hopefully the idea is not too complicated. I think it's definitely very tricky, right? let me also add some notes here. I mean, I think I'm not going to add notes on this one just because this is a very basic depth first search for the first answer, right? And then here, I think node and parent is self-explanatory, but parent nodes is basically the number of nodes coming in from the other side of parent, right? And then parent distances is the total distance of nodes coming from the other side of parents. And once you kind of do that, then you realize that, as we said, because now all those nodes advance by 1, so that's why we have a parent distance plus parent nodes, and that's it. The complexity pretty straightforward. We do a linear time transformation here. This is a linear time depth first search, and this is also a linear time tree traversal. So this is going to be linear time, linear space, and that's pretty much it, really, right? Yeah. But as you can see, I mean, I say that this is pretty straightforward, but obviously it is very easy to make mistakes, and you have to be really precise. But I think this one is actually not that bad, but I was just really bad about kind of defining everything. And I knew this going in though, so I really did want to get some practice here. Hopefully you find it useful in the struggle. How did I do it 2 years ago? Oh, I did it the same. I did actually do it with rebooting 2 years. Oh, it's only 1 year, 4 months ago. Huh. Oh, it's December. I guess so. I don't know. The years keep on running by me. But yeah, but this is basically it, and this is a very confusing. Wow. What is going on? All right. Well, if you watch that video, you're probably not gonna learn anything. But yeah. But before that, this is the way that I was talking about where it times out because it doesn't like the star graph will time this out because it's actually n square, which I did not realize at the time. But yeah, with the rerouting, which I actually did end up doing last time, even though the code is, I don't know, maybe slightly more confusing. But yeah, but maybe another way to write it is just that this is, and in a way it kind of reminds me a little bit of prefix sum, right? In that this part is just to calculate all the other nodes. It is just if you're given a node, it's just yeah. And here you can actually, this one, I think there are other ways around it, right? Because other nodes can, I mean, sure, you can include parents nodes and we do, but this is also just like you could probably do this and it's still the same, to be honest, because, so there are different formulation here, right? Because it's just the root tree minus the subtree, maybe plus 1, not even, okay, right? Just to make sure, yeah. So this one could be simplified, so you can kind of think about why other nodes. Other distances is a little bit trickier, but I think I was just being very silly about it because looking at this, it makes sense, right? Because this is just, well, this part is the incoming part, and then here, this part is the same subtree at node, and then the distance of v plus the thing is that basically this is the distances of the sum of distances from that branch elevated one level, and that's basically why we subtract from it, so that it gets the total distance from all the other branches, right? But yeah, I don't know. I'm not very. To be honest, I feel like I can solve this during a contest. I mean, because you just saw me do it, but it's definitely not fast, and I definitely feel like a lot of people are much better at it, and I don't even think that I explained this problem that well. But let me know in the comments. Let me know if you have any questions. This is not an easy one, at least for me. So yeah, subtree sum and count. What does that mean? Yeah, I guess this is the same way that I did it, except for they did it much slicker. Oh, I guess this is much smarter than the way that I did it, because basically it's saying that. Oh, that is smart. I see. I see. Okay, so I mean, it is the same idea, but just a easier way to represent this part, right? Basically, it is saying that okay, so we have um, okay, I see. So the way that this one is that okay, we have an answer for this. Answer being the sum of distances, right? So basically the idea here is that okay, you have the answer of node, right? And then now we know how many other. So the other nodes is going to be all the other nodes are the nodes that we add plus nodes, right? Because they move forward by one, and then we subtract subtree of re because these are the nodes that are closer. You get closer to one, and that's basically the idea. And maybe you don't even need other distances anymore. And then now, if you write it that way, then actually this is just answer sub re, right? And using this way, then you don't need to kind of use this to track the other distances. I guess this is, I mean, the way that I did is very bad, but I think that's why I need more practice as a result. I mean, the idea is the same, right? I mean, I think you saw that. Oops. Oh, I deleted the other nodes. Is that is equal to subtree of 0, which is n, right? Obviously, subtree of v. I think this is off by 1 somewhere, but oh, maybe not. Okay, I mean, yeah, I mean, I think the idea is still the same in how I came about it, but well, I mean, now it's no longer rerooting in a way because, I mean, it is a little bit because you're using answer of node, but I think the general structure of what I did actually, you get to reuse it in more difficult problems. But today I just kind of missed the obvious one. I think I was trying to get the same thing, right? Just to be clear, because basically this whole thing is other distances. Right, so if you kind of remember how I structured it, is equal to this thing. It's just that the way that I kind of, I mean, this isn't outer distance anymore, right? But I think other distances is like this, and then this is other distances minus the subtree, so that it gets it in the same idea that I had before. But yeah, what did I have? I feel a little bit dumb, to be honest. Right? So this is what I had before, and you can kind of see that it is the same idea, right? Except for I guess I move other nodes up here. So if you want to kind of just remove this, I am really dumb now that I think about it, but nonetheless, right? And this would be basically the same idea. Yeah, I don't know. Yeah, because basically I was trying to get. I guess I don't know what I'm doing. I mean, yeah, but I think the beauty of math sometimes is that there are multiple ways to the same answer, and and they're all mathematically equivalent. Obviously, otherwise it just won't work. But that's all I have for this one. I'm gonna try to delete one line so we could squeeze everything in one screen. It's close enough, right? Return answer. But that's all I have for this one. Let me know what you think. Thanks for watching. Stay good, stay healthy to good mental health. Wish me luck tomorrow and good luck on the contest. Stay good, stay healthy to good mental health. I said it again because maybe I need to get better mental health. I'll see y'all later and take care. Bye bye.